Imagine a computer so powerful that it could break modern encryption in seconds, simulate entire universes of molecules, and solve problems that would take our fastest supercomputers billions of years and yet. It operates not with one south and no south, but with something stranger, something that defies human intuition itself. Welcome to the realm of quantum computers, the most mind-bending and mysterious frontier of technology that humanity has ever created. Before we dive deep, don't forget to like this video, subscribe, and hit the bell icon. Because today, we're about to travel into the subatomic world, where logic breaks down, reality blurs, and the limits of human technology are truly tested. For decades, our digital world has run on classical computers machines that process information as bits, each bit being either a 1 or a 0. This binary system has powered everything from the first calculators to artificial intelligence and global internet networks. But no matter how powerful classical computers get, they follow the same basic principle: sequential, deterministic processing. Quantum computers, on the other hand, are built on the rules of quantum mechanics, the strange physics that governs the tiniest particles in the universe. Instead of bits, they use qubits, which can exist as both 1 and 0 at the same time, thanks to a phenomenon called superposition. This is like flipping a coin that's spinning infinitely in the air, being both heads and tails until it lands. But the real magic begins when multiple qubits interact through entanglement, another bizarre quantum effect where the state of one qubit instantly affects the other, even if they're separated by miles. Einstein called it spooky action at a distance, but in quantum computing, it's the foundation of a computational power that scales exponentially. 2 qubits can represent 4 combinations, 3 can represent 8, and with just 300 qubits. A quantum computer could represent more states than there are atoms in the observable universe. Think about that: a machine smaller than your fingernail could theoretically perform computations impossible for any classical supercomputer in existence. So how does this actually work? In a simplified sense, quantum computers use qubits made from tiny systems like trapped ions, photons, or superconducting circuits cooled near absolute zero. They manipulate these qubits with laser pulses or electromagnetic fields, controlling their quantum states to perform calculations. Instead of testing one solution after another like classical machines, quantum computers explore all possible solutions at once through quantum parallelism, then collapse to the correct answer when measured. It's not just faster computing, it's a fundamentally new way of thinking about computation itself. But before we start dreaming of unlimited power, there's a catch, and it's a big one. Quantum systems are incredibly delicate. Any small disturbance like heat, light, or magnetic noise can destroy their fragile quantum states, a problem known as decoherence. That's why most quantum computers operate in super-cooled environments, colder than outer space. Even then, they can only maintain their quantum state for a few microseconds. So building a stable, scalable quantum computer is one of the hardest engineering challenges in history. And yet progress is being made. IBM, Google, Intel, and startups like Rigetti and IonQ are racing to develop practical quantum machines. In 2019, Google announced it had achieved quantum supremacy, a milestone where their 53-qubit processor Sycamore performed a specific calculation in 200 seconds that would have taken the world's fastest supercomputer 10,000 years. Critics debated whether it was a true breakthrough or a PR stunt. One thing was clear: we've entered a new computing era. The implications are staggering. Quantum computers could revolutionize fields like medicine, where they might simulate molecular interactions to design new drugs in hours instead of years. In materials science, they could create superconductors that work at room temperature. In finance, they could optimize portfolios in real time. And in AI, they could accelerate machine learning beyond anything we can imagine. But there's also a darker side: quantum computers could break the cryptographic systems that protect our digital world. The RSA and ECC encryptions used in online banking, national security, blockchain could be cracked by a powerful quantum computer, exposing global data in seconds. That's why researchers are already working on post-quantum cryptography, trying to design algorithms that even quantum machines can't break. So, are quantum computers really the future? The answer is complex. Some experts say they're decades away from practical use. Others believe we're closer than we think. What's certain is that building them is testing not only our scientific knowledge, but but also the limits of human imagination. See, quantum mechanics itself is famously counterintuitive, tells us particles can be in multiple places at once, teleport their states across space, and behave differently when observed. When humans try to build machines on such principles, we're forced to confront how little we truly understand about reality. To put this in perspective, imagine explaining quantum computing to someone from the 1950s. They'd understand vacuum tubes, transistors, maybe even binary logic, but the idea of a computer that uses the wave function collapse of atoms to calculate answers would sound like pure science fiction. Yet here we are, building prototypes that can already outperform some classical algorithms. This shows that technology evolves not just by invention, but by pushing our understanding of nature's most mysterious laws. Now, let's take a deeper look at what makes quantum computing so challenging. One major issue is error correction. In classical computers, if a bit flips due to interference, you can simply check and fix it. But in quantum computers, you can't directly measure qubits without collapsing their states. So scientists have to use clever mathematical tricks called quantum error correction codes, where groups of physical qubits protect one logical qubit state. The result? To make one reliable qubit, you might need thousands of physical ones. This makes scaling up extremely difficult. Another problem is quantum noise. Because qubits are so sensitive, any vibration or electromagnetic wave can cause decoherence. That's why companies use ultra-cold environments, vacuum chambers, and even magnetic shielding to protect qubits. It's like trying to perform surgery during an earthquake. You need everything perfectly still. And then comes the issue of control. Manipulating dozens or hundreds of qubits simultaneously with precision. A single pulse error could destroy an entire computation. So why do we keep trying? Because the rewards are unimaginable. A fully operational quantum computer could simulate chemical reactions with perfect accuracy, solve optimization problems that classical computers can't touch, and even model the fabric of space-time itself. Some physicists believe quantum computers could help unify general relativity and quantum mechanics, the two pillars of modern physics that still don't fully agree. Others think they might uncover hidden patterns in the universe, revealing new dimensions of information itself. But there's also a philosophical side to all this. Quantum computing challenges our notion of determinism, the idea that every cause has an effect, every problem a predictable answer. In quantum systems, probabilities rule. Until you measure a qubit, it's both 1 and 0. Only observation collapses it into 1. This raises profound questions. Are we part of some larger quantum system? Is reality itself a kind of computation happening across infinite possibilities? And if so, is building a quantum computer our way of imitating the universe itself? Quantum computing demands control over matter at the smallest scales, precision that challenges physics itself, and energy conditions near absolute zero. There's a possibility that we might never build a perfectly scalable quantum computer, not because we lack intelligence, but because the laws of nature might not allow infinite coherence or control. Maybe this is the true limit of human technology, a boundary between understanding and impossibility. And yet, even if that's true, what we've already achieved is extraordinary. Just the act of building qubits, controlling them, and making them compute represents one of humanity's greatest scientific accomplishments. We've learned to turn the invisible dance of particles into logic. We've built machines that operate in a realm where cause and effect blur, and that alone is proof of how far human curiosity can reach. So as we stand on the edge of this new frontier, one thing is clear: quantum computers aren't just another step in technology. They are a leap into the unknown. They force us to rethink what computing means, what information is, and even what reality itself might be made of. Whether we ever reach full quantum power or not, the journey itself is reshaping science, its philosophy, and our very sense of what's possible. And maybe that's the ultimate message. The limits of human technology aren't defined by what we can build, but by how far we dare to imagine. If you enjoyed exploring this quantum world, make sure to like, subscribe, and share this video with your fellow science lovers. Because the future isn't just coming, it's already entangled with us.